Hello, everyone. I'm Kirsten Wakefield, Stakeholder Outreach Liaison for Maracus and MACAN. MACAN, the Mid-Atlantic Coastal Acidification Network, is co-coordinated by the Mid-Atlantic Regional Council on the Ocean and Maracus. We're a partnership of researchers, agency representatives, NGOs, and industry members working together to coordinate regional acidification monitoring and research to better prepare industry and coastal communities for changing ocean conditions. You've all probably heard of Project Bison, the largest land-based direct air carbon capture project in the US right now, expected to capture 5 million tons of atmospheric carbon per year by 2030. But most of our Earth is covered in water, oceans more specifically, that provide a vast space for CO2 buffering and carbon storage. We're just beginning to explore what opportunities might exist for CDR in that space and how those new technologies might help mitigate acidification on a local to regional scale. Today, we're really excited to bring together CDR policy specialist, Dr. Wil Burns, founder and CEO of Running Tide, Marty Odlin, and vice president and head of science at Vesta PBC, Dr. Grace Andrews, to discuss the current policy framework for marine CDR in our coastal states, innovative technologies being piloted that may help to mitigate acidification, and the challenges and lessons learned along the way. But before we get to the presentations, a quick look at our upcoming webinar series. Our April 24th webinar will highlight research from Dr. Jeremy Testa and project collaborators Dr. Ming Lee and Matt Weber to develop a coupled biological, biogeochemical, economic model to quantify climate change impacts on oyster aquaculture in the Chesapeake Bay. Registration information will be coming out next week. Our final webinar in May will feature vulnerability assessments and adaptation planning for the sea scallop fishery and Chesapeake Bay oyster restoration and aquaculture industry, as well as a comparison of climate resilience in wild versus cultured rootstock of the eastern oyster. But today, I'd like to give a warm welcome to our featured speakers, Dr. Wil Burns, Marty Odlin, and Dr. Grace Andrews. Wil is a visiting professor in the Environmental Policy and Culture program at Northwestern University and the co-founding director of the Institute for Carbon Removal Law and Policy at American University. His research agenda includes climate geoengineering, climate loss and damage, and the effectiveness of the EU's emissions trading system. Today, he'll discuss current and future international treaty regimes addressing governance of marine carbon dioxide removal and the role of U.S. domestic law at the federal and state level. Marty is the founder and CEO of Running Tide, a global ocean health company headquartered in Portland, Maine. As a systems engineer and member of a fourth-generation fishing family, Marty founded the company in 2017 after seeing the devastating implications of climate change on his own community. Today, Marty will discuss how Running Tide utilizes a science for action framework to develop and deploy the capabilities needed to both remove carbon at global scale and restore ocean and coastal ecosystems at the local level through interventions that include restorative aquaculture, macroalgae enhancement, and wild shellfish bed restocking. Our third speaker today, Grace, currently serves as vice president and head of science at Vesta PBC, advancing the research and development of an ocean-based CDR strategy called Coastal Enhanced Weathering. Previously, Grace worked for the Leverhulme Center for Climate Change Mitigation in the UK, where she led the design, execution, and analysis of the world's first large-scale field pilots of terrestrial enhanced weathering. Today, Grace will discuss how coastal enhanced weathering works to capture CO2, as well as lessons learned from the world's first pilots occurring right now on our eastern seaboard. Just as a quick reminder, we'll hold all questions until after the presentations. All participants will be muted, so please ask your questions via the Q&A box at the bottom of your screen. And Anthony Himes, our Sea Grant OA Fellow, will moderate the Q&A discussion. A reminder that this webinar is being recorded and will be available on the MACAN website shortly. So without further ado, let's turn it over to Wil.
Sought to govern ocean-based carbon removal, largely in response to ocean iron fertilization experiments in the last decade, where people were testing the potential impacts of putting iron in the oceans in terms of stimulating phytoplankton production. So in 2008, a convention called the London Convention, which regulates the deposition of materials into the oceans, passed a resolution related to ocean iron fertilization. And it was kind of a good news, bad news story for those that wanted to engage in it. The good news is that it said there's an exception under the treaty that if you're putting materials in the ocean for a purpose other than mere disposal, it doesn't constitute dumping, and you're not subject to the dumping regulations of the treaty, as long as it comports with all the other provisions of the treaty. However, what the parties ultimately concluded was that the purpose of the treaty is to protect the ocean environment. And to the extent that we know very little about ocean iron fertilization, we're going to narrowly circumscribe what can be done. And so what ultimately they said was that these ocean iron fertilization experiments could only ensue for purposes of scientific research, no commercial motivation, i.e. selling credits, for example, in the voluntary carbon market, and subject to a risk assessment framework. Next slide. And subsequently, the parties did develop such an assessment framework and provided that the nationals of any country that wished to engage in ocean iron fertilization were required to develop this framework and have it signed off on by national officials. Now, there were some real limitations about this resolution in terms of regulating marine carbon removal. The first is that it's restricted to ocean iron fertilization activities only. So some of the other marine CDR activities we think of, such as enhanced ocean alkalization or ocean upwelling or downwelling or seaweed farming, would not expressly fall into the rubric of this resolution. Though, of course, the spirit of it would suggest that if other approaches were to be deployed, the parties might decide that the same criteria should apply. The other major limitation is these resolutions are not legally binding upon the parties, though most of the parties adhere to most of these resolutions most of the time. Also, next slide, very recently, the London Convention and a treaty that's growing out of the London Convention, which will ultimately supplant it, called the London Protocol, identified other marine geoengineering approaches that they believe might have to be subject to regulation in the future. And that included two marine CDR approaches. That's macroalgae cultivation, and including artificial upwelling, as well as enhanced ocean alkalinity, and indicated that the parties may establish a regulatory framework for this in the future. So clearly, ocean-based CDR approaches are on the radar screen of the London Convention. Of course, one thing that the countries could consider doing is simply admitting that what they're doing is dumping and not be subject to the limitations that are placed by that resolution. In that case, many of these ocean-based approaches might ultimately be permitted as dumping operations, though some of them may face some serious challenges. For example, seaweed, because it might involve the use of persistent synthetic materials, for example, such as lines, might be restricted under the convention because it's prohibited in its annex. And so the countries or companies involved would ultimately have to determine that. There's another treaty called the London Protocol, which would have legally binding requirements that are similar to those under the convention. However, in the case of the United States, we are not a party, and those amendments have not come into force. Next slide. Another regime that mobilized during this time in reaction to ocean iron fertilization experiments was the Convention on Biological Diversity. And it also passed a resolution that indicated that any geoengineering activity, which is defined capaciously enough to encompass any of the approaches that we might talk about in terms of marine carbon removal, are also subject to essentially the same kind of requirements that the London Convention provided for. That is only for scientific research on a small scale and subject to risk assessment. Some of the limitations of the CBD resolution, however, include the fact that, again, it's not legally binding, and the United States is not a party to the Convention on Biological Diversity, and thus would not be subject to these provisions. Of course, the Law of the Sea Convention may ultimately in the future become pertinent. It has a number of provisions that talk about regulating pollution, which is defined as introduction of any energy or material into the oceans that may have harm to ecosystems or health. And to the extent that any of these activities might be construed as potentially posing those kind of risks, it could be subject to those provisions, which include liability. Next slide. There's also a new treaty that whose text was just agreed to, called the Biodiversity Beyond National Jurisdiction Treaty, and that treaty provides a number of provisions that might be pertinent in the future. This includes the requirement of environmental impact assessment for any activity that occurs in the open oceans, as well as next slide, provisions for area-based management tools. And again, those may in the future be pertinent to any activity that would occur on the open ocean. Okay, so we move from there to domestic law, and it should be emphasized that in terms of domestic law, ultimately both state laws and federal laws may apply. Next slide. One example of this is the Marine Protection Resources and Sanctuary Act. This is an act that regulates dumping of materials into U.S. waters beyond the territorial seas. It seeks to implement our obligations under the London Convention. And as you can see here, it declares that dumping materials in the ocean can be dangerous, and it seeks to regulate those activities. Next slide. The term itself, dumping, is defined broadly, right? It means disposition of material. And so again, it could encompass virtually any of the activities that we're talking about under in terms of marine CDR approaches. Certainly things such as ocean alkalization enhancement, for example, where the deposition of materials to enhance that alkalization is the very idea. Next slide. However, it also provides that dumping is permitted under some circumstances. To date, however, the areas that have been designated for dumping, and that's one of the requirements, is that an area be designated, have all been for dredge materials, with one exception for fish refuge. And so, in this case, any proposal for marine CDR approaches would likely run the gamut of permitting, right? And it would be a novel permitting requirement, and one that, quite frankly, the MPRSA really hasn't considered before, which is putting materials in the oceans, not just for the purposes of disposing of them, but for actually trying to prevent climate change and enhance the health of the oceans, right? And so this would be a case really of first impression in terms of the agencies, and I think the agencies are grappling with the implications of that. The MPRSA also provides for so-called research permits, and this might require some research experiments with some of these approaches that would not require the same stringency of permitting requirements if they were engaged in full-scale dumping projects. And so that's one avenue in which some of these activities might also ensue in the future. In cases where these permits might have direct effects on Native American tribes, for example, in terms of fisheries, we would also require consultation. In cases where these materials might be sourced through mining activities, such in the case of ocean alkalization, if it was done in domestic venues, laws such as the Clean Air Act, the Clean Water Act, and the Resource Conservation and Recovery Act would also be involved. In cases of enhanced ocean alkalization approaches that use electrochemical methods that might involve materials such as hydrochloric acid, for example, the transport of these would be subject to the Hazardous Materials Transportation Act. and also if there were storage facilities involved, the Emergency Planning and Community Right to Know Act. There may be some cases where these projects involve using materials for multiple purposes, including fill materials, such as for beach nourishment. Next slide. And in that case, it's the Clean Water Act, Section 404, might be pertinent, in which case it would be possible for the U.S. Army Corps of Engineers to issue a permit authorizing that, as long as it met all of the other requirements. Of course, the Army Corps would be subject to regulations such as the National Environmental Policy Act, so in terms of environmental impact assessments, Clean Water Act and Clean Air Act and so forth, and would have to consult with other pertinent agencies. And this would also include the Endangered Species Act. And then finally, again, just giving you a snapshot in terms of seaweed cultivation, in cases where there were anchored or floating offshore structures, it would require authorization from the U.S. Coast Guard in terms of potential navigation issues, be subject to the National Environmental Policy Act and the Endangered Species Act. In cases where construction was authorized in state waters, there would have to be consistency with state plans in the case of anchored or floating offshore structures, for example. Also, if these activities were done in coastal areas, there are also state laws often that deal specifically with aquaculture or seawater farming. This includes in Alaska and California, and on the East Coast in Maine and Connecticut. Notably, some of these states' aquaculture laws only provide for issuance of permits for shellfish or finfish, however, and don't anticipate permitting of seaweed cultivation at all. For example, this is true in New Jersey and Delaware and the state of Washington. And the statutes and regulations in this case don't expressly prohibit seaweed cultivation, but the lack of permitting guidelines may make those operations more difficult. And so I'm going to stop there and simply emphasize that at this point, there are a lot of ambiguities in terms of how we would construe how these activities would be regulated at the international level. Some regimes that simply haven't sought to take jurisdiction yet that may in the future. And at the domestic level, again, many of these approaches are extremely novel. They involve depositing materials under regimes that traditionally contemplate that these would always be pollutants that simply could harm those environments, and are ill-equipped in some ways to deal with activities that seek to use these to actually ameliorate environmental harms. And so the agencies are going to have to apply the standards that they have and potentially look to develop new standards in the future in terms of regulation. Thank you very much.
Thanks so much, Will, for that excellent overview of the policy framework at both the international level and at the state level as well, and what we have to look forward to in the future. I'm going to go ahead and turn it over to Marty. He's going to talk about Godzilla gigatons, and hopefully you can get your screen share working a little better, Marty. Thanks. All right.
1 second. Okay. Apologies. View. Okay. Oh, I seem to not be able to. 1 second. One minute. Okay. Can you see it?
Yep, that looks great, Marty. Thanks.
Okay, great. All right, thank you so much. The founder of Running Tide. Running Tide is an ocean health company. We're based in Portland, Maine. We're about 6 years old. And we work on restoring ocean health. So yeah, the talk is Godzilla, Goldilocks, and gigatons. Sorry. So everyone should be aware, but we'll just recap it on a few slides. Ocean health is in rapid decline. We've moved trillions of tons of carbon out of long-term storage in the slow cycle and emitted it into the fast cycle. And that's like basically the best analogy is we've unleashed a Godzilla, and Godzilla is just wrecking every community and wrecking everything that touches nature. And you know, for the ocean, that means the ocean's hotter, more acidic, and less productive than it's ever been, at least in human memory. You know, from a community-based perspective, I grew up in a fishing community, loved it, loved every minute of being on the waterfront. As a kid, the waterfront was full of people working, interacting with the ocean, feeding people, and all, you know, anywhere you go around the world, it's in decline. And, you know, this is not just in areas where you have overfishing and acute stresses from coastal pollution. Now it's happening in areas that where we had, you know, sustainable fisheries, and the collapses are being driven by non-direct human factors. So basically acidity and thermal stress. The two best examples right now are langoustine lobster off Iceland and the Bering Sea crab off Alaska, where we just seen like abrupt and radical collapse. Those crustaceans and invertebrates are particularly sensitive to acidification because they spend their larval stage of their life at the surface of the water. So where they can encounter more acute thermal and acidification stresses. So, you know, we don't have the data, but it's very, seems pretty logical that a sustainable fishery that collapses out of nowhere, that is that sensitive to acidification and thermal stress, you can draw the lines. So what I'm referencing here is all our systems, like human health, you know, this is our, like human health, Earth systems have a Goldilocks zone, not too hot, not too cold, not too much nitrogen in the water, not too little, not too, you know, pH not too high, not too low. Everything, every section of the ocean has a Goldilocks zone for life. And we're starting to bump up against it in a whole bunch of areas around the world. It could be like, you know, for the mid-Atlantic, you have the nitrogen loading in the Chesapeake. You can have thermal stress like we see in Maine quite often, or you know, acidification events like we're witnessing on some of the shellfish operations up in Maine. For fish, look, fish follow the Goldilocks zone. Mackerel was a massive fishery in Maine. It was always my dream to have a mackerel boat. But the mackerel are gone. They showed up in Iceland. They disappeared in Maine. They showed up in Iceland. And now the capelin are disappearing from Iceland and they're showing up in Norway. And like, yeah, fish are moving north. Data is incontrovertible, and they're moving deeper. The problem with fish moving north and deeper is that you run out of north and then you run out of shelf and then they're gone. So look, IPCC report, the latest report that just came out, or at least the synthesis report that just came out, is pretty clear. It's like incontrovertible now. We need massive scale carbon removal, massive scale mitigation of ocean acidification. There is no good future without it. Period. End of story. Center of Massive Science has spoken. And to do that, what does that mean functionally? That means transferring carbon mass from the fast cycle, upper layer of the oceans, atmosphere, biosphere, to the slow carbon cycle. How much material are we talking about moving? It's 1.7 trillion tons. That's 3 times the weight of everything on Earth. That's how much weight we have to move from the fast cycle to the slow cycle to restore us to pre-industrial levels. And we have to do that now. Like we're on a path to 3 degrees C of warming. 3 degrees C of warming is every single fishery anybody has ever done in a local environment is gone. Is it replaced by something else? Probably not. We probably don't have time to adjust to build the depth of ecosystem necessary to sustain any complex ecosystem. So, we're looking at the collapse, and IPCC report is pretty clear about this. We're looking at a high likelihood of collapse in local and coastal environments and onshore ecosystems as well. So the minimum that the IPCC report says is we need 660 gigatons of carbon. That will be the biggest industry in human history. On the timeline that we're talking about a $0 to $1 trillion industry, basically in 15 years, from $0 to $1 trillion in 15 years. That's like, there's no precedent in human history for anything to scale that rapidly. Certainly not in the physical world. The only thing that comes close is like internet queries on Google and things like that. Just like software things that scale really well. Nothing physical has ever done this. So what is Running Tide doing to support this? This is like a multivariate problem. So we've had to build an integrated system to attack it. Integrated system that includes, we have an integrated system that includes basically software systems, hardware systems, maritime operations, ecosystem design, ecosystem measurements. We have an agronomy and genetics team, fabrication and manufacturing, material scientists, data scientists, and ocean scientists. Pretty incredible team that we've put together. It's over 100 people now, global team. 65 engineers, 15 PhDs, and we're building what I'm pretty confident is probably the most sophisticated integrated system aimed at rebalancing the carbon cycle in the ocean right now. So first thing that we've built is a quantification system, measure the Goldilocks zone. First thing you have to do is measure the Goldilocks zone. So we've built a bunch of proprietary sensors. This one measures this is a fluorometer, a very low cost fluorometer that requires no calibration. We've redesigned all of the sensor stacks so they work. Low cost, no calibration. We can put them everywhere in coastal environments and offshore environments and understand what's happening with environmental and primary productivity data. We've coupled that with like a leading edge ocean modeling team that's developing all sorts of integrated models that help us understand the Goldilocks zone and the carbon flux through the ocean and how it's affecting that in ecological parameters in our area of operation. And then we've coupled that. So we have sensors, in situ sensors that we put out in the ocean. We have our models and we have our labs. And so we've built like onshore labs where we're able to measure in a more refined way, like how any intervention that we do, any carbon removal activity, whether it's ocean alkalinity or macroalgae growth or shellfish restoration, we can measure how that affects in a lab the chemistry of the ocean or in the biology of the ocean. And then with the environmental sensors and the models, we can put that together to create a data package that tells us what to do and whether what we did had good or bad effects. What does this look like? We've been deploying sensor buoys out in the open ocean. I think that we've reached a level where we say we have the first operable MRV system. MRV is like this really lame acronym for carbon removal that says measurement, reporting, and verification. It basically means, did you measure the Goldilocks zone? And did you measure the net flux of carbon across your entire supply chain? And can you eventually use that to offset companies' liabilities, their slow to fast cycle liabilities that they've generated. So we've built this incredible system. It's been 6 years to build it. It's like uses machine vision, a bunch of proprietary sensors, measures all sorts of biogeochemical parameters around these different activities that we can do. What that lets us do is enter this 5-step process. Where 5-step process to connect capital to nature. So how do you get paid to do this activity? How do you get paid to restore ocean health? The government is not putting out enough money to do restoration at any scale. Like there are some cool projects going on, but you're not talking about coast-wide or Earth system scale solutions. How you do that is you connect to the financial markets. And how we do that in how we're going to architect this entire system is you go through this 5-step process where first you diagnose. So you deploy sensors in coastal environments or offshore, diagnose what's happening in the ocean, diagnose where you're at in the Goldilocks zone. Then you develop an intervention. I'll explain our interventions in a second. You deploy that intervention and in the sensor system, you quantify the result, you quantify the change. So, you made an adjustment to the Goldilocks zone, you moved, you netted out a movement of carbon from the fast cycle to the slow cycle. And that's your quantification. You have packaged that up as a data product. Then you can monetize that and you can get paid by governments, philanthropies, you can get paid on, the voluntary carbon markets, compliance markets, what have you. It doesn't really matter, but someone's got to pay you to move that mass. And so all of that you have to build that around this, a pretty sophisticated set of sensors and understanding of how the ocean is been adjusted by the activity. So now I'll talk about some of the carbon removal techniques that we're using. We are very focused on using natural pathways, leveraging natural pathways. The whole world is a direct air capture machine if we nudge it in the right direction. So we don't need to build boxes around it. We can just use the world and use the natural carbon flows of the world and just nudge them forward through some minimally invasive activities. The two best ways to remove carbon in the world broadly, to move carbon from fast to slow, are photosynthesis and increasing alkalinity of the ocean. Those are the two largest carbon sinks on Earth. That is how the world removes carbon. And what that means functionally is like you either bury or sink biomass, so carbon in the form of plant matter, to the deep ocean, or you just bury it on land really deep or inject it underground, or you shift the balance of the ocean's kind of dissolved inorganic carbon pathways. So basically give the ocean an antacid effectively, and you can pull more carbon into the ocean. It's a simplistic way to say it, but it's like the simple way. Okay. For running tide, we're trying to, because you're trying to net out how much carbon you use, you have to use really efficient systems. So you have to get a lot of leverage. So our carbon removal system is basically, we make buoys out of materials that are non-exogenous to the ocean. Like here's one, I don't know if people can see this, but here's one of our buoys. They're about the size of a baseball. We make those out of materials on land, either minerals or we use like a waste biomass. You can use almost any biomass, but we'll make these little buoys out of it. They're very small. Transport them to sea on a boat. We drop them out in the sea, spray them with macroalgae spores, and we let them adrift. The minerals, the alkaline materials like limestone or olivine or what have you, will dissolve into the surface layer of the water. That is kind of that dissolved inorganic carbon pathway. The macroalgae will grow. The algae will grow and absorb carbon from dissolved CO2 from the surface layer of the water, collect on the buoy. Buoy infiltrates with water over a set period of time and then sinks to the deep ocean. So the buoys last anywhere from 60 days to 9 months, and we can tune that. We make sure that they end over the ultra deepest parts of the ocean, and when they sink, we're using gravity. So what's really nice is we use ocean currents to move it, transport it to the deep ocean. We use the sun to accumulate CO2 onto the buoy, or not CO2, but the carbon onto the buoy. And then we use gravity to basically compress it and bury it. So very, very efficient system to remove carbon. And, through that process, what's great about the process that we use is we utilize stochastic drift. So we spread these things out over huge areas. There's like a buoy every square kilometer. And you make a tiny, tiny adjustment to the Goldilocks zone in any given area. So like very distributed impact. but you have a big net effect on movement of carbon from the fast cycle to the slow cycle. So small local impact, big aggregate impact. Like the growing substrate is made from materials native to the ocean. Like, all these carbon removal pathways, what we're doing already naturally happen. Terrestrial biomass falls into rivers and gets transported to the deep sea on the order of 200 megatons per year. The biological pump of the ocean, algae growing and falling to the deep ocean, is happening all the time. And alkaline materials are constantly dissolving on land and getting into the ocean. So these are all the natural pathways that the Earth uses to rebalance the carbon cycle. We're just accelerating them. On top of that, we're doing a ton of research on algae, like marine algae. So we're built a huge data set of computational genomics for marine algae, sequence multiple strains of algae, understanding phytoplankton and, red algae, green algae, brown algae, a whole bunch of different types, really understanding what the effect they have on the ocean environment. We're pulling samples from all over the world in the deep ocean, seeing what naturally grows there, what will attach to things that are floating out there, and trying to really understand exactly what's the lowest impact way we can possibly accumulate carbon at the scale we need to, and move it to the slow cycle. Now, when we move into the coastal environment, there is a ton of activity that can happen. Transforming the world into a carbon removal machine and restoring coastal ecosystems and reducing acidification. So, we do shellfish enhancement in coastal waters. You can spread alkaline materials in coastal waters, like Project Vesta is doing this. This is a really cool thing. It still involves the same idea where you have a 3-part verification system and you're doing that 5-step process of that we talked about before to kind of measure, diagnose the problem and design an intervention, deploy it, quantify it, and then monetize it. And then you can start the loop over again. Like I said, $1 trillion industry is going to revitalize coastal communities. And it's also going to create all sorts of ancillary co-benefits, helping to mitigate the effects on fisheries in the short term and hopefully enhancing them over the long term. Running Tide has been, we've been at the kind of through the early stages and growing pains of this industry now for about 6 years. It's been a tremendous amount of work. But we've established a ton of engineering and academic partners. We have an independent science review board. We're working with multiple auditors. We're operating at ISO standards for carbon removal and for data integrity. There's just, we've been trying to pack as much insight into the team as possible and really make sure that we're right at the forefront of best available science and understanding of the ocean. All of these things, as they move forward, we need to have an enormous amount of data to understand what's happening in the ocean. And we need to engage really directly with these affected communities, because those are the people that, 1, have the knowledge, and 2, the capability to make these activities happen. So everywhere we go right now, we're in, Casco Bay, Maine, and we're in Akranes in Iceland. And these are we're engaging heavily in those communities and trying to work with them to find the best insights we can on how to do this type of work better. So yeah, I think just happy to, answer any questions. I think that the key takeaways for me, for people on this webinar are if we want to solve this problem, we need to connect capital to nature. You do that through data. You do that through deep understanding and measurement of what is happening. And then the second conclusion is we do this with communities. And if we do this right with communities, we can help preserve what we have and then bring back what we've lost, if we can do this fast enough and at a big enough scale. So yeah, connect capital to nature through data, understanding of what's happening, and the work is going to happen in coastal communities. So it's a fantastic opportunities for communities to re-engage with nature and the ocean. So thank you so much. Oh, Aaron, unmute.
There we go. Thank you. Thanks so much for that great presentation, Marty. We're going to transition into Grace's presentation now, and she'll be talking about a specific technology that's being used in the Mid-Atlantic on the Eastern Seaboard, and talking about some of the partnerships that they've made with coastal communities as well through Project Vesta. So I'll turn it over to Grace. Thanks.
Thanks so much. Okay. So thanks everyone for coming. As it was said, I'm Grace Andrews. I'm the head of science at a company called Vesta. We are an R&D company looking into specific kinds of ocean alkalinity enhancement. And the one that we pay most attention to is something called coastal enhanced weathering. So I thought for this webinar, I would spend a little bit of time talking about what this has looked like in practice to try and do R&D into these kinds of nascent and novel technologies. So a little bit about Vesta, like I said, so we are a public benefit corporation, and we currently have about 35 full-time employees, most of which are scientists. I'm very fortunate to be leading a team of, it's actually 13 now, PhDs with backgrounds from everywhere, geochemistry, such as myself, to microbiology, geomorphology, marine ecology, very interdisciplinary. And we are working with, again, really fantastic collaborators in our R&D efforts. And so we really have the benefit of some of the best scientific minds out there working with us on our R&D. Like I said, so we are really focused right now on something called coastal enhanced weathering. So this is a form of ocean alkalinity enhancement. There are, many different ways that you can try and increase the alkalinity of the ocean. This one is something that really got its start in the academic literature about 2 decades ago, but to date has really existed as modeling studies and laboratory work. So prior to Vesta's work, there hadn't been an actual field trial of coastal enhanced weathering. So that was really a primary goal when Vesta formed a few years ago, was to, ask the question, okay, lab work says this looks promising, modeling says this looks promising, but when we try this out in the real world, what kind of carbon removal efficiencies do we get? And what are the real world ecological impacts, either positive or negative? So the way coastal enhanced weathering works, fundamentally we use a mineral called olivine. It's a natural mineral, very abundant on Earth. You find it all over the place in the United States, basically the whole western coast of the US, but also really common in places like North Carolina, Georgia, and New York. And it is a special kind of mineral because when it dissolves in seawater, it takes CO2 out of the atmosphere. So it dissolves quite slowly. So this is a very gradual intervention. It dissolves over the course of really years, decades even. So one of the things that we really like about it is this is not something that causes immediate, large-scale, instantaneous impact. It's a carbon removal process that happens fast enough that it is meaningful for climate change mitigation, but not too fast. So we take olivine sand, we grind it into sand-sized particle grains, and we can match those grain size distributions to a particular location that we might be interested in working in. So we can really make these projects bespoke to the local environments. We then place that olivine sand onto coastlines in very specific ways, again, to try and maximize carbon removal efficiency and minimize impact. Like I said, that then dissolves, generates alkalinity, removes CO2, and of course, we then have to put a lot of work into measuring the carbon removal. And that is the MRV that you just heard Marty talking about. So again, olivine dissolves, that generates alkalinity in the ocean, draws down CO2. And again, this is a carbon removal process that happens naturally, sort of on geologic timescales. So this is already the main mechanism that regulates the Earth's climate. So we're really just trying to speed it up to have more short-term impact. Some of the things that are particularly exciting about this, like all ocean alkalinity enhancement strategies, that increase in alkalinity in the ocean draws a reduction in ocean acidification. So I don't have to tell this group, but that's a good thing for a lot of different reasons. The other thing that we like a lot about coastal enhanced weathering is it has another co-benefit of coastal protection. So right now, climate change, sea level is rising. We have pretty dramatic increases in coastal erosion happening, and that is threatening homes, livelihoods, and marine habitats as well. In response to that, particularly here in the US, we have a beach nourishment industry where we are adding sand back to coastlines to try and mitigate the impacts of climate change. This is climate adaptation. And so, every year in the US, we place about 37 million cubic yards of sand on our beaches for this purpose. And, you get projects as big as, say, 1 million cubic yard projects happening for coastal protection. So this happens in the US, but it also happens all over the world. And there's a really nice synergy here, right? We want to put sand on beaches to take CO2 out of the atmosphere, and local communities want sand on their beaches to counteract the consequences of climate change. So we see this strategy as something that is both climate mitigation, but also can contribute to climate adaptation, which is part of why it's really exciting. So we are at the point, as I said, we have been doing research, sort of foundational research into coastal enhanced weathering for a few years now. But as of this past summer, we launched 2 very small scale field pilots of coastal enhanced weathering. One was as part of a wetland restoration project. So we're interested in all sorts of different coastal settings, wetlands being one. Again, they're also subject to sediment loss, and restoration projects also often incorporate the addition of sediment there. So again, interested in whether or not we can add a component of olivine sand to wetlands to both improve the elevation, take CO2 out of the atmosphere, and potentially combine it with what are called blue carbon projects, and really use these projects as a multi-pronged approach to dealing with climate change. So we started that one in collaboration with the National Park Service, with Toll, and the USGS. But the other one we've done was a project directly on a beach as part of a beach nourishment project. So placing sand on a beach in Long Island. And this is one that we've partnered with the town, but also other institutions like Stony Brook University and Cornell Cooperative Extension. So I thought I would share a little bit more of the details about what this looked like to do this project here in New York. So this is some of the pictures from it. So we put down 500 cubic yards of olivine sand as part of the town of Southampton. Again, this is Long Island, their 10,000 cubic yard beach nourishment project. So this is a really pilot size project, right? 500 cubic yards on top of 10,000 cubic yards of dredged material. That meant the olivine made up about 5% of the total nourishment volume. And it was placed along about 1,000 feet of shoreline. And again, that was in July of this past year. So this is what the beach looked like a few months after. Here's the bulldozers on the beach, again, part of that beach nourishment project. And we have been monitoring the beach ever since. So we set up a design where we have both part of the beach that received strictly dredged sand, part of the beach that received olivine and dredged sand. And then we've been also, of course, monitoring outside of the project zone as control sites. Doing this project, of course, required quite a bit of stakeholder engagement. There are a lot of different stakeholder groups out there. Of course, one of them is really doing this in partnership with local academic collaborators. There are lots of good reasons to do that, including the fact that the people who are local to that site know more about the ecology and geochemistry and geomorphology than anybody else. So they're very good people to be working with to make sure that you're doing the best and most rigorous science. But we also engaged very deeply with just the local community. So, we got the word out in, local newspapers. We set up a high school internship program to make sure that we were involving the community and creating educational opportunities. We set up flyer boards and notice boxes with fact sheets about the project to make sure that anyone who was accessing the beach knew what was going on and knew how to reach out and learn more. And we have a quarterly newsletter that we send around giving updates on how the R&D program is going, highlighting some of our collaborations and the early results. And again, just making sure that everyone is aware of what's happening. And of course, this is all in addition to, speaking with NGOs and, doing webinars and that sort of thing. And we've gotten really positive responses from the community here. They are really excited about the project. We're actually having a plaque ceremony in the coming weeks to install a plaque at the beach, noting it as the site of the world's first pilot of coastal enhanced weathering. So that's the kind of reception that we've been getting, and it's been deeply rewarding. A little bit more about the monitoring that we've been doing. So we instigated a BACI design, so before after control impact, and we've committed to monitor the site for a minimum of 2 years, but that will change depending on the results that we gather. We're looking at all sorts of things from water to sediments, again, geomorphology, ecology, really trying to cover all of our bases, dot every I and cross every T, and make sure we get a really comprehensive understanding of what's been going on. And we've been getting really exciting results. So this is the map of the site right here in A, that's our site. And there are some other USGS monitoring stations nearby that we've been able to use the data from to understand the results from our own. But we've been looking at water quality metrics, things like chlorophyll A, pH, dissolved oxygen, and not seeing any significant changes due to the olivine treatment relative to some of these other control sites in the area. One I'll highlight in particular is pH. Obviously one of the goals of this kind of work is actually to increase seawater pH, but the expectation with a pilot this small is that it shouldn't move the needle on your overlying seawater pH. It's just too small to have an impact when you think about the small amount of alkalinity that these 500 cubic yards of sand are generating, mixing into an entire bay, ocean broadly of seawater. So it's just not enough to move the needle, and that's what we expected, and that's what we've seen. But we've been looking, of course, at benthic communities. This is a major point of interest because we are adding a sand to the beach that wasn't there before. So we have been doing a look at a benthic community structure. So we have some data from before the deployment, both in the olivine treated zone that's in green, and then our various control sites, that's the other colors, and then post-deployment at both the abundance and species diversity. And we're again getting really promising results in that following the deployment, there's no statistically significant difference between the abundances or diversity of species in the olivine treated zone relative to control sites. And that's actually particularly notable because generally speaking, doing any kind of beach nourishment can have an impact on species abundance. And the recovery timelines associated with that range from about 2 months to 2 years. So it's particularly promising that we, after 2 months, have similar abundance and diversity relative to sites that didn't have any nourishment at all. So that's really very encouraging. We've also done some work with oysters. I mean, again, oysters are a really important group to look at because of their importance for fisheries. And this site is not naturally a home to oysters, but we decided to do an oyster experiment where we actually went out and placed artificial oyster bags, again, within the project zone with olivine, and then outside of it in the control zones as well. And one thing that was particularly interesting to us is, of course, oysters are really good bioaccumulators of trace metals. So we really wanted, they're sort of the canary in the coal mine for trace metals. And so we really wanted to understand whether or not our intervention would have any impact on trace metals. And this was really the best method out there to get the answer to that. So again, we have data from 2 months post-deployment, control sites here, and then the olivine site in green. And again, when we look at the concentrations of various trace metals of interest, so we've got lead over here, copper, nickel, iron, these sorts of things, we don't see any statistically significant difference in the treatment site versus control. So again, a great result. And then, of course, we've also been looking at the impact in terms of carbon removal, right? At the end of the day, if you're not removing carbon, then this, there's no real point in doing it. So we've been tracking carbon removal. Again, one of our challenges is that the intervention is very, very small, and we're trying to generate alkalinity in the water column, but there is a lot of seawater in that water column relative to our intervention. So we've been dealing with that by deploying what are called benthic flux chambers, which are kind of like upside down buckets that you place at the sediment interface with seawater in it. And you put them out there for about a week. They're not permanent structures, and they allow for the accumulation of dissolution products, that alkalinity, for example, into the chamber, so that you eventually get to measurable concentrations. And this is some of the data that we found from, again, about 2 months after we did the intervention. Over the course of about a week, we see that pH of the seawater going up, we see alkalinity going up, and importantly, we also see that dissolved inorganic carbon concentrations stay the same, which is what you would expect, because we've just converted dissolved CO2 into alkalinity, so that doesn't change. But this is really important because, for example, this is the evidence that this intervention does generate that ocean acidification benefit that was predicted. So we do see that reduction, that increase in pH, as well as the evidence for carbon removal. So we are seeing evidence that this is an appropriate way to take CO2 out of the atmosphere, reduce ocean acidification, but we're not seeing negative impacts. So that's just a little bit about the pilot that we started. And as I said, that research is very much ongoing. And we will be, as we finish out that research, we're going to be submitting, for example, all of it really to the peer review process to make sure that we're being really transparent and open about the results that we've been generating. But we're also looking to do future pilots. So we have an objective, broadly speaking, of doing this kind of R&D work in a variety of different coastal settings to understand which ones might be a best fit for this kind of intervention. So hence marshes, beach nourishment projects. But we're also interested in moving a little bit more offshore and building other kinds of coastal protection structures with olivine. So we are currently in the permitting process for a project in North Carolina where we're looking to build what's called a berm about 1,500 feet offshore. So it's still very, very near shore, but it's a different kind of coastal protection structure. And we're doing this one, again, we've got some fantastic academic collaborators on board, a number of folks from the Coastal Studies Institute down in North Carolina, UNC Wilmington, and then also the field research facility for the Army Corps Field Research Facility. And this has opened up a whole bunch of new challenges, moving offshore versus right on the beach. We're looking at using amphibious vehicles to actually get out to the project site. The Outer Banks are an energetic environment, to say the least. So looking at how we can build hardware that is capable of doing the kind of monitoring program that we've done at the New York site, we'll be replicating that here again, showing you here our olivine treatment zone and our control sites that we've articulated. So this one, as I said, permitting is ongoing. So don't have a definitive answer there yet. But I guess to tie some things around to what we talked about with Will's presentation in particular, right now, permitting for these kinds of projects is very uncertain. Our particular kind of ocean alkalinity enhancement strategy is inherently designed to be tied in with beach nourishment and coastal protection projects of various forms. So for our project in New York, for example, we of course received local, state, and federal permits for that. And in that case, we submitted and received Clean Water Act permits. So it was part of a beach nourishment project. And so the permitting process did go through that pathway. And, we believe that that is the right pathway to permit these kinds of projects, which are fundamentally about building devices, right? These are structures that are being built to last for some amount of time. They are modeled after coastal protection projects, and that they were also trying to generate some benefits for coastal protection. And so, we think inherently that these kinds of projects are best permitted under things like the Clean Water Act rather than the NPRSA. But that's not to say, of course, that that's going to be true for all ocean alkalinity enhancement projects. And so, I'm very much of the mindset that when we talk about what kind of regulatory environment might be most appropriate for different kinds of marine CDR, it's easy to sort of conceptually try and lump them together and say, well, all ocean alkalinity enhancement projects should probably be permitted under, X, Y, or Z. But to me, that's kind of thinking about things, grouping things based on the outcome of the proposed project, which is to generate ocean alkalinity enhancement, for example, rather than permitting things based on their likely environmental impact, right? So there is a big difference, in my mind at least, between the likely environmental impact of a water treatment plant that is just, spitting out already generated alkalinity into a lagoon versus folks going out onto the open ocean with a boat and, placing rapidly dissolving instantaneous impact materials in the open ocean versus what we're doing, which is placing very gradually dissolving material onto coastal environments in partnership with coastal protection. Like they're all trying to get to the same place, the ocean alkalinity enhancement, but they're likely to impact the environment in different ways. And as such, should, in my opinion, be the permitting requirements should reflect the difference in those interventions rather than just trying to sort of group everything all together. So, but that's tricky, right? Nuance, we don't have a permitting regime anyway right now, and advocating for a more nuanced one it's a tall order, but I do think that will lead to the most appropriate permitting pathway. So that's sort of my 2 cents on the matter, but yeah, thank you.
All right, great. Thank you, Grace, and thank you to all our speakers for those great presentations. We have quite a few questions that have already come in, but if anybody else still has any questions they'd like to ask, please feel free to type them in the Q&A box as we go. Grace, that what you finished on there about permitting is a great segue into a couple of our questions here. So one, for Will, are there any kind of new proposals in place, or maybe other countries that have already navigated kind of some of those ambiguities you pointed out in the existing policy that may help provide some guidance on how to navigate this in the future?
Yeah, a lot of countries are still in very early stages of doing this. Germany has been particularly interested in regulating marine CDR activities within their exclusive economic zones. And so one of the things that they've done is they've actually implemented the London Protocol, incorporated it into their law, despite the fact that this amendment is not into place. And so they they've set up a risk assessment process. They limit marine CDR activities that would deposit materials into coastal areas to those that are natural. That's going to be one of the ongoing sort of issues on how one defines natural, right? We struggle with that issue a lot in terms of CDR, with what is a nature-based solution and what is not, what is an industrial solution, right? So I guess probably most people would construe macroalgae harvesting as nature-based. What is ocean alkalinity enhancement, right? Is it nature? Is it a hybrid approach? Is electrochemical ocean alkalization, because it involves more infrastructure, not nature-based, right? Those are things that are going to have to be worked out. But for the most part, there haven't been a lot of countries that have actively engaged from a regulatory standpoint. And I think it's important that those that are engaged in the open oceans do engage with these international treaty regimes, because if we're talking about stakeholder engagement, when you're on the open oceans, your stakeholders are all of the nations that are potentially affected in terms of fisheries interests, navigation, and so forth. And the way to engage those are through regimes such as London and the Convention on Biological Diversity, both of which have thoughtfully started looking at these approaches and are establishing regulatory frameworks that should be engaged with. I'm not comfortable having Ocean Visions or NGOs or even academic institutions be the ones that ultimately make these decisions, or certainly the private sector, right? We need public engagement through those regimes, and we haven't had enough of that yet, in my opinion.
Okay, great. So Grace, you kind of spoke to this already at the end of your talk, but this is also open to you, Marty. Could you speak to the permitting process that Running Tide has needed to follow for your activities? And Grace, feel free to add anything else you'd like to for Vesta.
Yeah, it's a lot harder to help the world than to destroy it. I'll tell you that. It's pretty easy to keep doing horrible things. And, I just want to point out that, you can fly a plane around the world and 30% of your emissions end up in the ocean. And that's not dumping. But if you do anything to help clean that up, could be considered dumping. It's kind of, insane, but it's just the irony of all this is we've got this it's a lot harder to do this activity than you'd think it would be. So right now, to date, Running Tide has 62 permits that we've got through to conduct different levels of experimentation, starting in coastal waters and then working our way towards offshore deployments. And most of the work we've been doing offshore has been in testing and calibrating sensors and understanding biogeochemical parameters, so that then we can take that information, bring it to the lab, and then mimic that offshore environment, because it's been so difficult to get permissions to do this offshore. So most of the offshore work we're doing is actually in the lab. I mean, we have a bunch of sensors out in the water because it's easy to get permitted. So you can do a lot of calibration and understanding what's happening out there, but to do any of this at scale right now, you're pretty much constrained to labs. So we've spent millions and millions of dollars building up facilities that can mimic the offshore environment, so we can run these tests, and then we can only correlate that to very small scale sensor deployments. But yeah, it's been 60, pretty much what we've done. We're constantly limited by permissions. So this entire effort around the world is completely gated by permissions. Technically, scientifically, engineering standpoint, system performance, we're, the base science is hasn't changed on how we think the ocean works. We have all these sensor systems. We have capabilities. We're completely gated to scale this up by permissions. And it looks like that will be the death of this industry at current trajectory. no one will be able to build up this industry to the scale of the problem under anything remotely, like any permission structure that exists right now. We will not be able to do what the IPCC says we have to do. So I just want to be really clear, like the equation doesn't pencil out. You can build these companies and you can do carbon removal, and that looks like that's going to happen, but we're not going to solve the problem. But anyway, yeah, so most of the work we've been doing has been working in the coastal environment, getting offshore, starting to do and just to run these activities so far has been 60 permits that we've had to land, and looks like it's just going to be permits and protocols forever gating these activities scaling up. So Christine can talk about what they're working through.
Yeah, getting permits is definitely a massive challenge. That's absolutely true. The timelines associated with them, I should say, are also really challenging. I mean, we are all very small startups that are running on very tight budgets, trying to do the best that we can, and stay afloat while we develop the R&D here. It's the permitting processes that Vesta has gone through, I have to say, have been at both state and federal levels very rigorous. I have spent a lot of time talking to regulators, and I think that's how it should be, right? I do believe that these things need to be appropriately regulated and thoroughly vetted. I think that's important for a lot of reasons, including social acceptance. For any of these technologies to scale, for this industry to scale, the public has to have confidence in the fact that that these projects and these technologies have been deeply looked at and carefully evaluated. That's a necessity. So it's, for me, I very much think that regulatory oversight is critical to the success of the rigorous regulatory oversight is critical to the success of this. It's the ambiguity about which permit do you apply for? And once you do, do the agencies who receive that permit know what to do with it? Or do they give it to a different agency? Like that ambiguity and the slowdown and timeline associated with it, that's, for me, that's been the biggest challenge. But that is, that's the start of a nascent industry, I suppose. But yeah, trying to stay afloat while we work with regulators to figure this out and land on an answer that again helps promote the industry and makes sense and is scalable. This is a collaborative process. But yeah.
Right. Can I add something about this narrative? I worry about a crisis narrative that talks about the world burning, because the world is burning, right? Unchecked climate change is a major challenge in terms of oceans and in terms of terrestrial environments. But the problem with the world is burning sort of narratives is, if you take the wrong approach, you're pouring kerosene on a burning environment. You can make things worse. And the National Academy of Science last year, in their CDR, Ocean CDR report, emphasized that we're at very early stages in terms of the research, and we have to be extremely careful, because some of these approaches at very large scale could potentially wreak havoc with ocean ecosystems. For example, large-scale seaweed cultivation. There's a study last year that said it could attract enough organic subsidies that would ultimately result in faunal consumption and release of CO2 that could result in a net increase in CO2 in the environment, right? We know that massive introduction of seaweed into deep sea ocean ecosystems, where we know very little about those species at this point, could wreak havoc with these ecosystems. We have to be careful. We need regulatory systems that carefully vet these. And so it's not mutually exclusive to say the world is in a lot of trouble, but we have to proceed slowly. And it would be great if we had 100 years to be able to do that. but we are going to need substantial periods of time to assess these processes. And the same is true with enhanced ocean alkalinity, where we're worried about alkalosis impacts on some species. We're worried about bioturbation. There's just a lot of things we don't know. We don't know a lot about MRV at this point. We're nowhere near Goldilocks. And so I see the frustration of those that would like to move faster. But I think the regulatory environment is trying to facilitate research, but at the same time trying to protect all interests. And if we don't get this right and we beget a backlash, we're ultimately going to have this industry shut down in early stages and not potentially get some of its benefits.
Okay, so Marty, you touched on this. One of our other questions was, are we concerned about changing the ocean chemistry at the bottom of the ocean by moving massive amounts of carbon? And has anyone explored those consequences with deep ocean species? So for you, Grace and Marty, if either of you have any more information on that, it'd be great to hear it.
Yeah, look, I mean, that's every aspect of this needs to be studied in depth, which is why I've spent 6 years building the best available tools and the best available network of sensors that can be put out there to understand this. Of course, you have to contextualize any additional impact that you're having against the baseline first, like how much material falls to the deep ocean, how much organic material falls to the deep ocean every year. Okay, what's the addition of a small amount of that, and what will the impact of that be? Of course, super critical questions. We approach this we've approached this through systems design, like mitigating that impact is something we've approached through system design to distribute things over huge areas and make really small effects on the surface and on the bottom. At the limit, sure, at the limit for anything, there's going to be impacts that we're going to have to adjust to, but we've committed like a serious crime of thermodynamics to put this much release the spring of slow carbon into the fast cycle. And we're gonna, there's gonna be a tremendous amount of disorder that gets created as we recompress that spring. The question isn't, do you create disorder somewhere in the system? Is there a perturbation in the system? Of course there's going to be. That's what the math says will happen. It's a function of like, how do you do that in a way that, the system can absorb to least deleterious effect? So yeah, there's been a tremendous amount of work understanding the biological pump in the ocean. The work of Jim Barry has done a lot on biomass falls to the deep ocean, understanding the effects that has on the local environment. Presumably at some massive scale, even with a distributed system, you can make adjustments that are measurable on the deep ocean. But we're so far from that, like we're never, like we can't, we are so far from any deleterious effect that's measurable, like so far, I can't even express, like to get there, at least with our system, the way we've penciled it out, we would be the biggest company in the world before we got to that point where we'd even measure a deleterious effect. Like just the size of the operation would be like so massive. And, I get that people want to get perfect before you start, but that's not how engineering works. You have to proceed and learn. And, we've spent 6 years and we've spent, tens of thousands of hours of engineering time to build these sensors. And the only way we make them better is to go do the thing. You can't get better in the lab on paper describing it. You have to go exercise that. You have to do the exercise in order to learn from it. So yeah, my concern now is for sure we're going to measure all these things, but to do these benthic studies at scale are hundreds and hundreds of millions of dollars, maybe billions of dollars. To do really good benthic studies of the deep ocean to understand like, a 1% addition to the biological pump of the ocean, I'd say hundreds of millions, if not $1 billion in funding. And right now we're not spending fractions of that. We spend more money in the US on lawnmowers than we do on CDR research, let alone ocean CDR research, despite it being the most, according to the IPCC, one of the most important things we can do as a species to stay alive. So, there's a limit to how much study we can do with the resources we have. All we can do is do the best we can, build the best systems we can with the resources we have, and then hope to be able to proceed to take the next step and to gain the additional resources needed to do those studies. So we're not going to have perfect answers because we don't have enough money. That's like it's like the short answer. We just don't have enough money. So if the government wants to give me a few $1 billion to go like do these studies, happy to go do it first. But the reality is, you know, these things happen in steps where you take a small step, you learn a little, take another step, you learn a little more, take another step, learn a little more. So that's the journey the startups are on. But they're, you know, gated a lot of these concerns, including like large scale benthic impacts. Like there's no way to gain that data until you go do it and then get the sensor systems stacked up and the resources to be able to go do large scale studies.
Okay, so we have time for one more question. So Grace, this will be for you. Have you done any calculations yet on how much sediment volume you would need to add for a nourishment project to see a discernible change?
A discernible change in pH, for example. Well, this sort of regardless, for any nourishment, you know, sort of traditional beach nourishment, so in a real sort of open coastline. So the sort of maximum scale you get there in terms of total beach nourishment volume that anyone might want to add, say, is like 1 million cubic yards. Like that exists out there as a 1 million cubic yard dredged material project. We would never advocate for making that all olivine sand. You know, one of the sort of founding principles of what we're doing here is that olivine sand can be an addition to these kinds of projects, so that we're not fundamentally changing the sediment composition away from its natural condition, or any other part of the sediment dynamics. So olivine will always just be a percentage of those projects. So I don't know, even at like called the most upper end, maybe you have 20% olivine, you know, you're still only talking about, you know, 200,000 cubic yards of olivine in a particular project on a particular length of coastline. And even with that kind of scale, and sort of, you can model out residence time and stuff, you don't move the needle on seawater conditions in any meaningful way. The way that this works to generate kind of meaningful changes in seawater pH, you know, that's really when the whole industry has to get to scale. That is a global endeavor that will take a lot more than just olivine on beaches or, you know, pipes into, you know, coastal environments or ships in the ocean. You know, any one of these alone is not really going to move the needle here. It's about all of these approaches combined really working at that global scale. So honestly, sort of to Marty's point, the R&D pathway for these strategies should start small. You know, we've started with 500 cubic yards, which is very small. And, you know, we believe the right approach here is gradual and phased increases in that to look at increasing levels of complexity and scale. But the good news is, even when you start getting to sort of, you know, large, meaningful scale, you know, to put in Marty's words, when you do the math, you really don't see local changes. You really need to hit that global scale sort of intervention to move the needle. So, yeah.
All right. Well, thank you all for that great discussion. Unfortunately, that's all the time we have for questions today. So with that, I will turn it back over to Kirsten to wrap us up.
Oh, you're muted.
Thank you guys so much for giving us your time today and sharing your perspectives and your experiences and the permitting challenges that you've been facing, and really helping us kind of understand this journey that you're on to go from starting up to scaling up and all the challenges that you're facing along the way. I think this conversation has been really helpful for the MACAN community as all this stuff starts to come on board, and we're learning more about it as we go. So I really appreciate the time that you guys gave to us today. And the recordings will be posted up on the MACAN website in a couple of days. So if you want to go back and look at anything or have further questions, feel free to reach out to us as well. So thanks so much for your time and have a great day.